Hello and welcome to another video on the exercises of the course of machine dynamics. Today we will look at some animations on the topic balancing of rigid rotors. For this exercise we will consider a certain rotor as shown here, which is mounted between two bearings, rotating with a constant angular velocity. In this case, for example, if this was a perfectly balanced rotor, we would assume that the center of mass of this rotor would lie on the rotational axis, and also the principal axis of this rotor would be the same as the rotational axis here. But generally, this is not the case. So in a general case, we would have a system like this, where the center of mass here has a certain offset to the rotational axis, and also the principal axis, the yellow one, is not parallel to the rotational axis, the gray one here. So we have a certain centrifugal force, which is the single arrow, and a certain inertial moments, which is the double arrow here. And as a consequence, we would observe certain bearing forces, x2 and y2, and x1 and y1 at the other side, depending on the coordinate system. And these would be the equations derived from the moment theorem and the angular moment theorem. So we have four equations that we can solve for the four bearing forces here and here. And we would end up with those expressions, assuming now that we have a constant angular velocity. In those expressions, we still have the deviation moments and also E, which is the offset of the center of mass from the rotational axis. These are quantities that we don't know in advance. So in order to balance this rotor, there exist several techniques that we will have a look on the next slides. And one thing to mention that you can also find in the lecture notes is that we can replace the system, so a system with a certain center of mass, deviation moments like this, by using a system like this, which is a system now with a perfectly balanced rotor, but added two individual masses at two different planes. We have centrifugal forces here, but we don't have deviation moments anymore. And this system is dynamically equivalent if we find the correct values for the masses and the angles of those equivalent masses. So in order to balance the rotor, we distinguish between two techniques. And the first one that we will have a look on is the force measuring technique. For the force measuring technique, we would have to operate the system in the subcritical region, which means that we assume very high stiffnesses at the bearing points or very low angular frequencies. And for this technique, it's necessary to measure the forces here and here by means of certain techniques. And then we can use the equation here, which gives us a relationship between the complex forces. So complex because we have a certain amplitude and a certain phase shift that we have to consider. So a relationship between those forces and T1 and T2, which are the centrifugal forces of the equivalent masses that we have to add to the system. So the balancing masses, I mean. And in this expression, we have the values L and A, which are also added in this sketch here, that are assumed to be known. And then we can find the green balancing masses as a result. So from the T1 and T2 quantities, which are again complex, we can determine the masses and the angles of those balancing masses that have to be added to the system in order to balance it. So we don't have any bearing forces anymore here because we have added the bearing masses. And then if we would calculate the total center of mass of the system, so from the yellow and the green masses, that would now be at the center, so at the rotational axis, and the principal axis of this rotor, including the green masses, would also be the same as the rotational axis here. So we have a perfectly balanced system. The other technique that we distinguish is the distance measuring technique. So the displacement measuring balancing. Here we have a system where we have the bearing points that allow 1 degree of freedom in horizontal direction in this case on both sides. So it's possible to measure the displacements x1 and x2, which are also complex, so they have a certain amplitude and a certain phase shift. And in our original system, we know that we have center of mass, which is not on the rotational axis, and also the principal axis is not on the rotational axis. But what we can see here, if we operate now in the supercritical region, is that the rotational axis at the ends would only move in vertical direction. So it's possible now to find a relationship between x1 and x2, so between the displacements at both sides and the imbalance of the system, u1 and u2, that needs to be compensated. So in this expression, the alphas, these are some coefficients that are still unknown. So we have to determine those coefficients before. And for this, we do 2 calibration runs. The first run where we add 1 calibration mass on one balancing plane. And later we will do the same on the second plane. So in the first plane, we will add this known defined unbalance that we can characterize by u1 0, so 0 because there's no mass on the other plane, and u1 is assumed to be real instead of an imaginary value, because without loss of generality, we can assume an angle of 0 for this mass. And then we can use the formula from the slide before, measure x1 and x2, which are the displacements here and here, and determine alpha 11 and alpha 21. We do the same thing for the other side. So we again have a defined unbalance at this side, again with an angle of 0, so we have a real value here for u2. And then we can use the same formula, but now have an expression to determine alpha 12 and alpha 22. So we have determined all alphas from the alpha matrix, and we can go back to our original system where we don't consider a perfectly balanced rotor yet, but certain rotor with an unbalance. And then we can invert the alpha matrix here. We can measure the displacements x1 and x2 for this system and have now an expression, if we invert the matrix, for u1 and u2, which is the imbalance of this system that needs to be compensated by balancing masses. So from u1 and u2, it's possible to find an expression for the masses or radiuses and for the angles for the two balancing masses that we have to add. So if we add the balancing masses at the balancing planes here and here, that might look like this. So we see that we don't have a displacement of the rotational axis anymore at these points. And what we can say for this perfectly balanced rotor is that the center of mass of the total system, so of the yellow center of mass, the original one, including now the green balancing masses, then the total center of mass would be on the rotational axis in the middle. And the principal axis, which was yellow here before, including the two balancing masses, the green ones, would then be the same as the rotational axis in the middle. So this is the end of this exercise video, and I thank you for your attention.